for hyperbola, eccentricity is greater than 1. And hyperbola is this. We have two branches, and again, the first one is we'll look at is in Cartesian coordinate system. Okay, with the origins at the centers. So this is our Cartesian coordinate system X, and this is center, and this is 1. So these are two branches, and these are focus. Here is 1, 2. So the first approach is definition using the constant here before is, say here we have an object P here, and an object, let me call that a point P, at point P. So this is the R1, and measure from here, oops. This is R2, okay. And earlier we have derived that R2 minus R1 equal to a constant. If you remember, I remember that one, I kind of described to you that kind of historical derivations, and for some reasons, this derived is in this quantity. And A is an intrinsic negative value to make the whole thing positive, okay? So here we adopt this notation. This is the notation used in our textbook. If you have the time to read the textbook, actually you have to. And when you go to the hyperbolic section, then you can see they use minus. And don't feel weird. Simply A is an intrinsic value of the negative value there. So under these situations, then R2 minus R1 can be become this. R2 equal to x plus c squared plus y squared, and then R1 x minus c squared plus y squared. And what is c? So let me give you the, so this is minus a, this is minus c. And again, don't feel weird. The distance is always positive. So here A, C, they have an intrinsic value, negative value. Okay. So with the AC those things, then basically here we have the derivation is x squared divided by x squared. And already we have utilized is b squared equals c squared. Okay, so that is the equation for describing hyperbola. And we using the second definition, focus directrix properties. This is the focus directrix properties, and let me use different figures to show in details. So this is the one branch. Let me pick the right branch there. And again, we're still on the Cartesian coordinate systems. And the directions. So any point, and let me say the point is here. R1. So this is R2. Okay. So the distance to focus in the ratio to the distance to the right track should be constant. And here E is positive. And let me give certain parameters. This is minus D. And from here to here, this is minus K. And from focus, minus C. Okay. And the intersections of the focus to the orbit, so this is defined as, we call it P. So clearly the P is we define as the parameters. The parameter actually is the distance, vertical distance from a focus to the orbit there. Okay. The same thing, if we have a light, sorry I forgot to draw it. So if this is the focus, then simply this distance is P. From here to here, that is the P. Okay. So with these things in mind, and then here we, again, we repeatedly apply this property to two particular points, and one is at P1 here. The other one is at P2. And then I want to derive a useful properties for our calculations. So with this one, R1, R2 equal to E. At point P1, we have E equal to R1 is this one, so that distance from here simply is minus C plus A. Minus C minus A, right? Again, this distance is R1, basically is the difference between the two things. So that is this one. And divide by R2, what is R2? R2 is this one, so that is minus A minus D. And then at point P2. So at P2, then R1 becomes this one, so that is P. Can we take this P earlier for ellipse is B squared divided by A, but here everything is intrinsically negative, so here we put a minus here. Okay, I use these properties for calculations. So here is P R1 and R2 is from here to here, so that is minus C minus D. So from the two things we can have is D equal to A squared over C, E equal to C over A. So with those things, and then we can have this. M equal to minus C plus D. So again, here for some reason, this is and from the focus, the distance between the focus and the directrix is n. So this one can derive by is this, and p we know is minus b over a, so that is a minus e squared, and RP again we use the equations of the orbits, and here we see whether I can derive it. Anyhow, so here using the equation of the orbits is this. That is a quickest way. Okay, and RA is the equation of the orbit when mu equal to 180 degrees. So that is P 1 minus E. So that is AE plus 1. So this one, yeah, okay. So with those things, again, we have a similar tables. Let me modify it here. Let me use different color to indicate the difference. How about that? So this is E minus 1. This is the same. That is the same like this one. It's a minus here. Okay, that should be like this.